Welcome to Water Resources. Today we're going to talk about climate change, and we're going to focus on a very specific set of data. These are temperature observations that have been integrated from all over the globe, and they are some of the most compelling, direct, observed evidence of climate change. Although there's some, obviously some analysis and reduction of these data. What we're going to look at here is the actual temperature data for the Earth. This is the temperature of the Earth. So we have all over the globe for hundreds of years, thousands of weather stations where we've recorded temperature. These are on land. We've got buoys out in the ocean. There have been manual measurements over the centuries of both things by people that have been recorded very faithfully through time. And so what has been done, what this graph shows you is temperature, what we call temperature anomalies from 1880 to 2017. And if you take every temperature observation from 1910 to 2000, so from about here, 1910, let me get my laser pointer turned on, from 1910 to the year 2000, every temperature observation everywhere over the globe was averaged together, and that average doesn't matter what the absolute number it might have been. Let's just say it was 60 degrees hypothetically. I don't know, but let's just say it was 60 degrees. So we say that the average temperature for that 90-year period was 60 degrees Fahrenheit. We're going to say that is the global average temperature during that time, and that represents a zero anomaly. If you have any individual year in that period and you average all the temperatures for that year from land and ocean and everywhere, and that year's temperature comes out to be 60, then we would say it's zero anomaly because the average is 60 and that year was 60, so the difference between the two is zero. If we average a different year and that year comes out at 59, well, 60 minus 59, or 59 minus 60 is -1, so that would be a negative anomaly, meaning that's a colder than average year, and it would be one degree colder than average. Same thing, if the average temperature for a given year was 61 degrees, we'd say that's a +1 anomaly, so it's 1 degree warmer than average. Now, why do we use these anomalies instead of the absolute temperature? Why don't we just put on this graph instead of 0, 60 degrees? Well, because that's a little misleading to say 60 degrees. 60 degrees is the average for all the temperature all over the globe, but that's not the average temperature, say, for all the weather stations in Missouri or Minnesota or Texas. You would expect that in Minnesota, if we just looked at Minnesota data, the average temperature there would be a few degrees colder, probably, than Missouri, because it's further north. And if we looked at the average temperatures for just all the stations in Texas, well, Texas tends to be a little further south and a little further west, and probably would be a little bit warmer than Missouri. But if we say that it was 1 degree warmer than normal, we can take, if we live in Texas, we can take whatever the average is in Texas over the long term and add 1 degree to that, and that gives us an idea. Well, it's usually 63 degrees in Texas, and this year it was 64, right? Because it's 1 degree warmer than average. And the same for Minnesota, it might only be 52 degrees there on average, so 1 degree warmer there is only 53 degrees. So that's why we use the anomalies. It's a way of normalizing the data for everywhere on Earth, and then looking at it in a very objective, fair way. So these are data. These are temperature observations. The only thing that's been done is filtering out some, maybe some bad observations where a thermometer broke or something and was giving some weird reading, saying it was 89 degrees in the middle of the winter in Antarctica. You throw that data out, it's obviously bad. Everything else, you get in there, you average it, and you weight it geographically, because if you have 10 weather stations in Springfield, Missouri, you're not going to compare that to one station in northern Montana. You're going to average the 10 together in Missouri, in Springfield, and call that one. And Missouri will still have a lot of different stations, and Montana might have a different, but you geographically weight things so that you don't bias the data that way either. All right, then we have that anomaly. All right, then we can go back and we can calculate the average for every year in our record. Let's just take this year right here. Looks like 1908. This one right here. That looks like it's just about the coldest year on record. The scale here, unfortunately, we don't know where -1. It's probably about here on the scale. They don't have it marked. But I'm guessing that this coldest year, 1908, was about 0.75 degrees, in this case Celsius, below the long-term average. So that's the coldest year in the record. This year, 2017, is about 1.5 or maybe 1.4, 1.5 degrees warmer than the long-term average. So that's sort of our range. Our hottest year is about 1.5 degrees above the average, and our coldest year is about 0.75 degrees below the average. Now, I want you to think for a second. If we graphed anomalies like this, where above average numbers are red lines that go up off of the zero line, and below average years, our cold years, are blue lines that go down from the average line, and the climate was not changing. If we assume an unchanging climate, then what would this graph look like? You might even pause the video here for a moment and think about that. What would you expect? How would you draw this graph hypothetically if the climate was not changing? All right, so we're back. I hope you paused for a moment and thought about that. You might think, well, if the climate was unchanging, everything would just be a zero and there'd be no red or blue lines. But that's not really right if you think about it a little further, because you know that with or without climate change, weather varies day to day and year to year. Not every January is as cold as every other January. Not every July is as hot as every other July. Even if the climate's not changing, that's going to be true because weather varies day to day. Over the long term, the averages would be flat. You'd have that net average of zero difference. But what we would really expect in an unchanging climate with this graph is that we'd have something like what happened here from about the 1940s through the 1970s. We'd have periods, we'd have a few years where it was warmer, and then we'd have a few years where it was colder, and it would flip back and forth over time because warming and cooling trends tend to come in cycles. We'll have a few warm years, a few cold years. Sometimes we have a really cold year right next to a warm year, and it might flip back again after that. But the point is, not only would we have sort of equal chances through time for warm, cold, warm, cold, warm, cold, but the magnitude of those warmth and cold years would be about the same. You'd see that the depth of the blue lines was about equal to the average height of the red lines. And that's sort of kind of what you see here in the middle part of the 20th century. In this case, that trend, if that's what we saw for the full 130-year record here, we'd say there was no change in climate. But because we only see this in the middle, what's happening is, what this graph is telling us is that the average temperature of the Earth has been increasing pretty steadily over the last 130, 150 years. And that ever-increasing trend intersected the long-term average for this period in the middle part of the 20th century. So what we had is we have an increase, I guess if I do it this way, it matches the graph, an increasing temperature average through time. But when we compare that to a long-term average, they intersect. Where my arms cross is what happened here in the 50s. And so for a while, we had equal chances of warmer or colder because the long-term trend was exactly what the long-term average was. But then by 1980, the trend had surpassed the long-term average. And what we see is every year before 1940 was colder than almost every year after that, and certainly colder than every year after 1977 or 1978. Every year since 1977 or 1978 has been warmer than nearly every year since before, and certainly every year before 1940. You think about this, the warmest year in this period, 1880 to 1940, was 1939. This last blue line there, it's barely below the zero line. Every year since 1978 has been warmer than that. Not just warmer, pretty significantly warmer. It looks like maybe 1979 or 1978 here. This point on the graph is probably the coldest year since 1977 or 78, and that's probably a tenth to 0.15 degrees warmer than the warmest cold year before that. So what you see now is, since about 2000, our coldest year since 2000 is warmer than our warmest year pretty much any time before that period. Of course, it looks like 1998, which was an El Nino year. You take El Nino and you pop the effects of El Nino on top of the climate change trend, and for a while there, 1998 was the warmest year on record. But these coldest years in this period are warmer than even the coolest. The coldest years in this period are warmer than the warmest years in the previous periods. This is exactly 100% what you would expect to see if the average temperature of the Earth was increasing due to climate change. Okay, we'll talk more about climate change, but I wanted to spend some time on this really important graph, which is some of the most clear, best evidence of observations that demonstrate the overall changes in the climate. All right, thank you.